Refraction of light. You would probably have noticed that a spoon placed in a glass of water looks bent at the surface of water when viewed obliquely. Also, when a pencil is dipped in a glass of water, it appears bent from the surface of water. This bending of light as it travels through different media is called refraction. The two media, in this case water and air, have different optical densities. Ordinarily, a ray of light will travel in a straight line through medium of uniform optical density, say air. Its speed is 3 times 10 to power 8 meters per second. However, if a ray of light is shone through water from air, the path of the ray appears bent. This shows that a ray of light changes its direction of propagation as it travels from air to water. Equally, a pencil partially dipped in water appears bent or broken to the observer. When a ray of light passes from air to water, its speed changes. This causes a change in direction of the ray. By definition, refraction is the change of direction suffered by a ray of light as it passes obliquely from one optical medium to another with different optical densities. Notice that wherever a ray is incident on a surface separating two media, a small fraction of the light always gets reflected. Refraction can make an object appear to be in a different position. For the same reason, the part of the pencil which is submerged looks as if it has moved away from the part above the water and it appears broader. Now let us understand what is going on by looking at ray diagrams. A ray of light will bend towards the normal whenever it travels from a rarer media to a denser medium. Here, IO is the incident ray, OR is the refracted ray, I is the incident angle, and R is the refracted angle. In this case, incidence angle is greater than the refracted angle. Next, a ray of light will bend away from the normal whenever it is traveling from a denser medium to a rarer medium. IO is the incident ray and OR is the refracted ray. I is the angle of incidence and R the angle of refraction. In this case, however, I is less than R. Now, the following are components of a ray diagram. Incident ray is the ray of light striking the surface of separation of the media through which it is traveling. The normal is the perpendicular drawn to the surface of separation at the point of incidence. The angle of incidence is the angle which the incident ray makes with the normal at the point of incidence. The angle of refraction is the angle which the refracted ray makes with the normal at the point of incidence. Refracted ray is the ray of light that has changed its direction at the surface of separation when traveling from one medium to another. Now I want us to perform an experiment to see how light is refracted when it's incident on a rectangular glass block. We place a rectangular piece of glass block on a white paper fixed on a drawing board. Trace the boundary A, B, C, D of the block. Now remove the glass block. Draw an incident ray IO. Draw a normal N1, N2 at the point of incidence O. Fix 2 pins on the incident ray IO. Carefully replace the glass block within its boundary ABCD. Looking from the other side of the glass block, fix 2 pins such that the feet of all the pins are in one straight line. Remove the glass block and the pins. Mark the pinpoints P1, P2, P3 and P4. Join P3, P4 to represent the emergent ray O'E. Join O'. O' is the refracted ray. Measure the angle of incidence, angle of refraction, and angle of emergence. Angle of incidence is greater than angle of refraction, and angle of incidence is equal to angle of emergence. Extend O'E backwards. You notice that the emergent ray is parallel to the incident ray. Now to sum up, this experiment simply shows you that when a ray of light is passing from air to glass, that is, from a rarer medium to a denser medium, the refracted ray bends toward the normal, drawn at the point of incidence. The emergent ray O'E is the refracted ray emerging out of the glass block. O'E is parallel to the incident ray. This means that the refracted ray has been displaced from its original path by a distance xy. This is referred to as lateral displacement. We also observe that angle O' N1' is equal to angle R and that angle E is equal to angle I. That is, angle E is greater than angle O'N'1. Thus, a ray of light bends away from the normal as it travels from a denser to a rarer medium at the point of incidence. From this experiment, if performed accurately, we can deduce the 2 laws of refraction. And the first one is rather obvious, that the incident ray, the refracted ray and the normal at the point of incidence all lie on the same plane. It is also found that the ratio of the sine of the incident angle to the sine of the refracted angle is a constant. That is, sine I over sine R is equal to a constant. This is called the Snell's law, and the constant is called the refractive index, denoted by N. Now you can try this with various angles of incidence and measure the corresponding angles of refraction. If you do that and then plot a graph of sine I against sine R, you will obtain a linear graph through the origin. The gradient of this graph is the refractive index for that material. Now let us look more into this refractive index. Consider a ray of light traveling from medium 1 to medium 2 as shown on your screen. For the two media, sine I over sine R is equal to the refractive index N. The constant N is the refractive index of medium 2 with respect to medium 1 for a ray of light traveling from medium 1 to medium 2, and it's written as N1 to 2. Therefore, sine I over sine R is equal to N1 to 2. N1 to 2 depends on both medium 1 and medium 2. Notice that this type of refractive index is relative. Why? Because it compares one medium to another. By the principle of reversibility of light, a ray traveling from medium 2 to medium 1 along the same path would be refracted, making the same angles. Thus, sin R over sin I is equal to N 2 to 1, where R now becomes the angle of incidence. Sin I over sin R is equal to 1 over sin R over sin I. From equations 1 and 2, it follows that n 2 to 1 is equal to 1 over n 1 to 2. That is, they are reciprocals of each other. Let's take an example. Calculate the refractive index for light traveling from air to glass, given that N glass to air is equal to 0.67. In the solution, N for air to glass is equal to 1 over N glass to air, which is equal to 1 over 0.67. And that would give us roughly 1.5. Let's take another example. A ray of light striking a transparent material is refracted as shown on your screen. Calculate the refractive indices of A, N1 to 2, and B, N2 to 1. In the solution, N1 to 2 is equal to sine 75 degrees over sine 47. If you complete that, you get 1.32. N2 to 1 is the reciprocal of N1 to 2. Therefore, we have 1 over 1.32. If you complete that, you get 0.757. Final example. Calculate angle I on your screen given that the refractive index N air to water is 1.33. In the solution, 1.33, the refractive index, is equal to sine I over sine 45. If you complete that, sine I is equal to 1.33 times sine 45. Then we have sine I is equal to 0.9404. Get the inverse of that. I is equal to 70 degrees. So why does this light bend? When the ray of light falls at an angle on a glass, some of the light is reflected. The rest passes into the glass. The light bends in one direction as it enters the glass and in the other as it emerges from the lower edge. It is this shift in direction that we call refraction. But what happens? Think of light as a series of waves. This ripple tank is sending parallel waves across its surface. Putting a plastic plate in water makes this part of the tank shallower than the rest. Waves travel slowly in shallow water. This change in speed changes the wavelength. The wavelength at the top is shorter than at the bottom. When the plate is at an angle, the wave also changes direction. The wavefronts change direction when they reach the plate. To understand how speed can cause a change of direction, imagine a truck approaching a marshy ground. If the marsh is at an angle, the right wheel slows fast. The left carries on its speed for longer, swinging the truck around. So when light hits a glass block, it changes direction because it changes speed. And so we can express refractive index in terms of velocity. Consider the wavefront of a wave crossing the boundary from medium 1 with the speed v1 to medium 2 with speed v2, where v1 is greater than v2 as appears on your screen. At the interface, the wavefronts are refracted since the motion is slower in medium 2 than in medium 1. Suppose the wavefront XYZ takes time t to move to position XY', Z'. In medium 2, the wavefront covers a distance ZZ', which is equal to v2 times t, while in medium 1, it will cover the distance XX', which is equal to v1 times t in the same time t. Now, dividing XX' by ZZ' would give us v1 over v2. However, sin θ1 is equal to XX' over YY', while sin θ2 is equal to ZZ' over YY'. Dividing the two ratios, sin θ1 over sin θ2 is equal to XX' over ZZ'. Therefore, sin θ1 over sin θ2 is equal to v1 over v2. But then again, n1 to 2 is equal to sin θ1 over sin θ2. Therefore, n1 to 2 is equal to sin θ1 over sin θ2, which is equal to v1 over v2, where v1 and v2 are constant for a given pair of media with particular wavelengths. Refractive index can therefore be given in terms of velocity by the equation n1 to 2 is equal to velocity of light in medium 1 over velocity of light in medium 2. When a ray of light is traveling from a vacuum to a medium, the refractive index is referred to as the absolute refractive index of the medium, denoted by n. Vacuum has a refractive index of 1. Absolute refractive index n is equal to velocity of light in vacuum over the velocity of light in a material. In practice, the velocity of light in air is used instead of velocity of light in vacuum, since air has a refractive index very close to that of vacuum. Refractive index of a material is therefore given by n is equal to velocity of light in vacuum over velocity of light in a material. If c is the velocity of light in air, v1 the velocity of light in medium 1 of refractive index n1, and v2 the velocity of light in medium 2 of refractive index n2, then N1 is equal to C over V1. Therefore, C is equal to N1 V1. Also, 2 is equal to C over V2. So C is equal to N2 V2. Comparing equations 1 and 2, N1 V1 is equal to N2 V2. Therefore, NV is equal to a constant and is equal to velocity of light in air, C. Now, N1 is equal to velocity of light in air over the velocity of light in medium 1. N2, on the other hand, is equal to velocity of light in air over the velocity of light in medium 2. N2 over N1 is equal to the velocity of light in medium 1 over the velocity of light in medium 2 equal to V1 over V2 equal to N1 to 2. Correct? Therefore, N2 over N1 is equal to N1 to 2. Again, from the wavefront that we've just seen, N1 to 2 is equal to sine theta 1 over sine theta 2. But then N1 to 2 is equal to N2 over N1. Therefore, N2 over N1 is equal to sine theta 1 over sine theta 2. And therefore, N1 sine theta 1 is equal to N2 sine theta 2. So n sine theta is equal to a constant, where n is the refractive index of the medium and theta the angle between the ray and the normal in that medium. This is the general statement of Snell's law. Now let's take two examples. Calculate the velocity of light in diamond given that the refractive index of diamond is 2.42. Take the velocity of light in air to be equal to 3.0 times 10 to the power 8 meters per second. In the solution, and the refractive index is equal to velocity of light in air over the velocity of light in diamond. Therefore, 2.42 times the velocity of light in diamond should give us 3.0 times 10 to the power 8. If we divide that by 2.42, we shall have a velocity of 1.24 times 10 to the power 8 meters per second. The next example. Calculate angle theta given that the velocity of light in water is 2.26 times 10 to the power 8 meters per second and in glass is 2.0 times 10 to the power 8 meters per second. In the solution, N water to glass is equal to 2.26 times 10 to the power 8 over 2.0 times 10 to the power 8, which gives us 1.13. But then we know N water to glass is equal to sine theta over sine 30 degrees. Sine theta is equal to 1.13 times sine 30, which gives us 0.565. If we do the sine inverse of that, we get theta is 34.4 degrees. So a straight pencil PQ, when immersed obliquely in water, a portion of it appears to be shortened and raised up as P1 Q1 under the water. Let's get a ray diagram. Rays of light from the point Q are traveling from water to air. As the rays of light are traveling from a denser to a rarer medium, they bend away from the normal. After refraction at the surface, they appear to be coming from the point Q1. Now, during spear fishing, the fisherman aims at the tail of the fish. When a fish in clear water is viewed at an angle, its image appears ahead of its actual position as it is raised up due to refraction of light from water to air. So if the fisherman aims at the head of the image, the spear will certainly miss hitting in front of the actual fish. But if the aim is at the tail of the fish, it's likely to hit the head of the actual fish. Another effect of light refraction is the apparent twinkling of stars, and you probably have observed this at night. But do they really twinkle? The truth is no, stars do not twinkle. The rays of light coming from the stars travel through different layers of air of varying density. These rays get refracted continuously and bend towards the normal as the refraction is from a rarer to a denser medium. The movement of air and convectional currents causes a change in the densities of layers of air. As a result, the position of the image of the star keeps on changing after every short interval. These different positions of the image formed at short intervals of time give the impression that the star is twinkling. Again, at dusk or dawn, the sun appears to be larger than at noon. This is because when the sun is near the horizon, the rays of light coming from the sun have to pass through layers of air of increasing density. Due to continuous bending of rays, the sun appears to be larger. At noon, the sun appears smaller. This is because the rays of light that fall normally on the surface of the earth do not get refracted at all. Real and apparent depth. Now, it is a common experience that a water tank appears shallower than it actually is. Also, a coin at the bottom of the tank appears closer to the surface than it actually is. It is due to the refraction of light that the apparent depth of the water tank or any object inside it is less than the real depth. Let's say an object O is lying at the bottom of a tank containing water. A ray of light AO incident normally is reflected from O along the same path. For this ray, angle of incidence is 0 and therefore the refraction angle is also 0. How about another ray OB? That on refraction into air appears to be coming from O'. Therefore, a virtual image O is formed at O'. Hence, the depth of the tank seems to be AO' instead of AO. From Snell's law, we have W mu A is equal to sine I over sine R, which is equal to sine of angle AOB over the sine of angle AO'B. This gives me AB over BO, everything over AB over BO'. If you cancel that out, we'll finally end up with W mu A is equal to BO' over BO. Since the aperture of the eye is very small, the two rays from A and B will enter the eye only if B is very close to A, and hence BO' is approximately equal to AO'. AO' is the apparent depth. BO is approximately equal to AO. AO is the real depth. W mu A is equal to 1 over A mu W. It's just the reciprocal of that. So if W mu A is equal to BO prime over BO, then A mu W is equal to the reciprocal of that, which is equal to BO over BO prime. Thus, refractive index is the ratio of real depth to the apparent depth. Now, having done all that, I want us to look at this experiment here. We have here a piece of glass and we want to see the refraction of light incident to the glass-air interval for various angles of incidence. So for a ray that is incident, normally it is reflected along the same path. In this case, the angle of incidence is 0 and also the refracted angle is 0. Now let us increase the incident angle gradually and look at the refracted ray. So clearly refraction is taking place at the glass-air interface. And as we increase the incidence angle, the refracted angle also increases. Notice that the refracted angle is greater than the incident angle at any point. Increase the incident angle and see what will happen. Now it reaches a point where the incident angle produces an angle of refraction of 90 degrees. That is, the refracted ray appears along the surface of the glass. This angle of incidence that produces an angle of refraction of 90 degrees is called the critical angle. If the incident angle is exceeding beyond the critical angle, refraction does not occur. Rather, all the light is reflected in the medium and obeys all the laws of reflection. This is called total internal reflection and can only occur at the interface when light travels from a denser medium to a rarer one, like from glass to air. So you see, by the time we get an angle of refraction of 90, some rays are already reflected inside the glass. So again, you see total internal reflection occurs until we get to that critical angle and the refracted ray emerges perpendicular to the normal. So for this media, the critical angle is around 40, 41, 42 there. Anything less than that and the normal refraction takes place. Perfect. Now let us look at how we calculate the critical angle and total internal reflection, and in this case we are going to use a water-air interface. So the refractive index of air is 1, by now we know that, and that of water is 1.33. Then we have a ray of light traveling from water to air, that is from a more to less optically dense medium. So it strikes the water-air interface, and of course we expect refraction or reflection to occur. But if we have the incident angle being equal to critical angle, the light will not emerge from either side, but will be refracted on the interface. And that means that we have this angle of incidence which have produced an angle of refraction of 90 degrees. And we want to know what angle of incidence produces an angle of refraction of 90, because that is the definition of the critical angle. And we want to see how we can calculate that. And first we are going to derive the equation for the critical angle. Now this is Snell's law. N1 times sine of theta 1 is equal to N2 times the sine of theta 2. And N1 sine theta 1 is the incident side, and n2 here, n2 sine theta 2 is the refraction side. I want to find out what this angle theta 1 is. So I'm going to take out this theta 1 and replace it with theta c. Theta c being the critical angle, and now we can solve what theta c is. So if I divide both sides by n1, I shall have sine theta c, the sine of critical angle, is equal to n2 sine theta 2 over n1. Now you notice on the left hand side I already cancelled out n1. Proceeding, I know n1 and n2. I also know theta 2 is 90. So sine theta c is equal to n2 sine of 90 degrees. Now divide by 1, and the sine of 90 is also 1. So divide by 1 the refractive index of air, that is n1, and again I know the sine of 90 degrees is 1. So I can simplify this expression. I can cancel out this sine 90 and replace it with 1. So I get sine theta c, the sine of critical angle, is equal to n2 over n1. Now you got to remember that n2 is the refractive index of the material on the other side. In this case it is the air. n1 is the refractive index of the material on which the light is initially traveling before hitting the boundary. So for our case, n1 is 1.33, refractive index of water. And this is the expression for calculating the critical angle. So let us finish our calculation. What incidence angle do we need to produce a refraction angle of 90 degrees for a water-air interface? So we have sine theta c is equal to 1 over 1.33. Sine theta c is equal to 0.75. Sine theta c is 0.75. Now this is not the critical angle. To get the critical angle, we get sine inverse of 0.75, and if I do that, I get theta c, the critical angle, is 48.6 degrees. So if I shine a light so that it makes an angle with the normal line of 48.6 degrees, it will travel along this boundary. If I increase the angle of incidence to greater than the critical angle, then I will have total internal reflection. That is when all the light is reflected off that boundary. So for a water-air interface, the critical angle is 48.6 degrees and will always be that. Now this concept is important in fiber optics. We want to make sure that when we send our phone calls or internet, or all the stuff that we do is transmitted through the cable without getting out. So we have to have an angle. The critical angle must be greater. If we shine the ray on that critical angle, it will travel along this boundary. But we want to shine it so that it's all reflected in and we have total internal reflection so that we don't lose any signals. Now the fiber optic cable has two parts. That's the core, which usually has a refractive index of about 1.62, and then there is a special layer called the cladding or the clad, and the clad has a lower refractive index of about 1.52. In order to have total internal reflection, this refractive index must be lower. With this setup, we now calculate the critical angle. So sine of critical angle is equal to n2 over n1. We know this from the previous example. Hope you remember what n2 and n1 represent. n2 is the refractive index of the cladding. So we have sine of critical angle is equal to 1.52 over 1.62. And if you do that, you get sine of the critical angle equal to 0.938. Finding the sine inverse, we shall have theta c, which is the critical angle, is 70 degrees. So if I increase this angle slightly, I'm gonna have total internal reflection. And that's basically the principle behind the fiber optics. Now, finally, we look at the effects of total internal reflection. Now, we have seen that total internal reflection is the reflection of light that occurs when it strikes an interface at an angle of incidence that is greater than the critical angle for the pair of media. Some of the effects of total internal reflection include formation of mirage and the sparkling of diamond. Let's start with the mirage. Now, if you have ever traveled on a flat sandy ground on a hot day, you might have noticed that there appears to be a pool of water far ahead. And this often confuses travelers in such areas to think that there is water ahead. Also, if you travel or drive along a tarmac road, far ahead there appears to be pools of water. But in truth, there is no water. This phenomenon is called a mirage. A mirage is an optical illusion seen very often in deserts, during which an observer sees inverted images of distant objects. The observer is led to think that the inverted image of far-off object is the reflection of the object in water. So how does it happen? In hot places like deserts, as the sun gets heated, the lower layers of air becomes hot and the upper layers are comparatively cooler. A light ray coming downwards from any object passes through the layers of air of gradually decreasing density. At each layer, refraction takes place and the light rays bend away from the normal. The angle of incidence continues to increase until at a certain layer, where the rays are incident at an angle greater than the critical angle of the layer of air with respect to another layer of air. At this interface, the light suffers total internal reflection and proceeds upwards from the rarer to the denser layers of air. The entire ray is therefore concave as shown here. Consequently, the observer will see an inverted image of the object. The observer thinks there is a pool of water from the formation of the image. A similar scenario is observed on a tarmac road on a hot day, where the observer sees the images of the clouds and thinks there is water ahead. Sparkling of diamond. Now, a diamond stone sparkles as the rays of light suffers total internal reflection at various phases. The critical angle for a diamond-air interface is 24 degrees, which is very low. Thus, most of the incidence rays suffer total internal reflection. Moreover, diamonds are usually cut with their faces in such a way that once a ray of light enters it, it suffers total internal reflection at various phases before it has any chance to emerge. Wherever the angle of incidence at any phase is less than 24 degrees, the light comes out from it and the diamond appears to be bright. Thus, a ray of light on entering the diamond literally gets trapped within for some time and causes it to sparkle.
By the 1890s, things really started to hot up. In those times, guys like William Crookes, various other experimenters, all started playing with this new phenomenon of high voltage using a device called a Ruhmkorff coil and passing this high voltage through tubes that the air had been exhausted from. So in other words, they had removed the air from these tubes and they tried to see what would happen if very high voltages were passed through the slot. Now, there is our cathode ray. You can see the ray appearing across the tube. This is the sort of thing that fascinated the scientists of those days. Now, this is very interesting because this led to all sorts of things. And of course, if you continue to experiment as they were doing, what would happen? Discoveries are bound to be made. And this, of course, led not only to the discovery of the electron, but also the discovery of something that I'm sure a lot of us have had dealings with in one way or another, the discovery of X-rays.